Universal Law of Gravitation. Do you know that the rings of Saturn, which appear so solid, are not really rings at all? They consist of countless chunks of ice and rocks, ranging in size from enormously large to tiny grains of sand, each circling the planet in its own individual orbit. The force that created and preserved the rings is the same force that binds us to the Earth's surface, that is, gravitation. Since ancient times, observation of stars, planets and their motion have been the subject of attention in many countries. The biggest milestone in this endeavor was the discovery of universal law of gravitation by Newton in 1686. With just one simple equation, he described the force of gravity and showed that the same law of gravity is also applicable to the moon and to other astronomical objects. Newton also determined the orbits of planets, moons and comets. About 2000 years ago, Greek philosopher Ptolemy proposed geocentric model, according to which all celestial bodies, including the stars, the sun and the planets, revolved in circular orbits, and the Earth was at the center. In 1543, a Polish monk, Nicholas Copernicus, proposed a different model, according to which all the planets moved in circles with the sun at the center. That is known as heliocentric model. However, a more elegant model in which the sun was at the center around which all planets revolved was already mentioned by Aryabhatta in the 5th century AD. German mathematician and astronomer Johannes Kepler formulated three laws of planetary motion, also known as Kepler's law of planetary motion. He realized that Copernicus' concept of circular orbits about the sun had to be abandoned. According to Kepler's first law of planetary motion, planets move around the sun in the elliptical orbits, that is, flattened circles with the sun at one of its focus. This is also known as law of orbits. According to his second law of planetary motion, also known as law of areas, line connecting the sun to a planet sweeps equal areas in equal times. If A1 is the area swept by a planet in a given period of time near one focus, and A2 is the area swept by the planet in the same period of time near another focus, then the planet swept equal areas. The importance of Kepler's second law is that though the orbit is symmetric, but the motion is not. A planet speeds up when it is approaching the sun, gets its greatest velocity when passing closest to the sun, and speeds down when it is moving away from the sun, and gets its lowest velocity when passing at the farthest point from the sun. According to Kepler's third law of planetary motion, also known as law of periods, the square of the orbital period of a planet is proportional to the cube of its mean distance from the sun, which is half the sum of the smallest and the greatest distance from the sun. It has been said that Newton was struck on the head by a falling apple while sleeping under a tree. This accident was considered to inspire him to predict that perhaps all bodies in the universe are attracted to each other, and so was the apple attracted to the earth. Newton then analyzed the motion of the moon around the earth and concluded that the force governing the motion of the moon is same as the force that attracts a falling apple to the earth, that is, the gravitational force. He further concluded that similar to the Earth-Moon system, a gravitational force causes the motion of the planets around the Sun. He proposed his law of gravitation, according to which every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. If the 2-point masses A and B of masses m1 and m2 are at a distance r from each other, then, according to the law of gravitation, the force of attraction on point mass B due to another point mass A is proportional to the product of their masses and inversely proportional to the square of the distance between them. Hence, the magnitude of the force is proportional to the product of the two masses upon the square of the distance between them, or the magnitude of the force is equal to g times the product of the two masses upon the square of the distance between them, where g is the proportionality constant known as universal gravitational constant. Direction of the force is towards the point mass A. The force law given by Newton is often referred to as inverse square law because the magnitude of the force varies as the inverse square of the separation of the point masses. The same can be verified by varying the separation between the two masses. The law of gravitation applies only to the point masses in which the entire mass of a point mass is supposed to be concentrated at a point. Symmetrical bodies, such as a sphere having uniform density, can also be considered as point mass, as their masses are also concentrated at the centers. In such cases, distance r is the separation between their centers. In formulating his law of gravitation, Newton used the following observations. For the circular motion of an object, a net force, that is, the centripetal force, had to be acting on the object because, without such a force, it would move in a straight line path rather than in a circular path. For example, if we tie a stone at the end of a string and whirl it around a circle as the stone moves, direction of its velocity changes continuously. That indicates it has acceleration. According to Newton's second law of motion, a force is the cause of an accelerated motion. Since the string can only pull the stone, therefore, the force exerted by the string is towards the center of the circle, and if we leave the string, it will become loose. It will no longer pull the stone, and the stone will move away along a tangent to the circular path. The pulling force required to move an object in a circular path is also called the centripetal force, and the corresponding acceleration is called centripetal acceleration. If an object of mass m moves with a uniform speed v along a circular path of radius r, then its centripetal acceleration can be measured as v square upon r, thereby its centripetal force can be measured as mv square upon r. A planet moves around a sun in an elliptical orbit, but in most of the cases it is very close to the circle. Therefore, Newton considered the orbit to be circular and measured the centripetal force, that is, the gravitational force that the sun exerts on a planet when the planet moves around it. By knowing the total distance covered by the planet around the sun, that is, the circumference of its orbit and its orbital time period, orbital velocity of the planet can be measured as 2 pi r upon t. Hence, centripetal acceleration due to sun's gravity, A, comes out as 4 pi square r upon t square. And the corresponding centripetal force becomes 4 pi square m r upon t square. If two planets of masses m1 and m2 are separated from the Sun by the distances r1 and r2 respectively, then the gravitational forces exerted by the Sun on them are 4 pi square m1 r1 upon t1 square and 4 pi square m2 r2 upon t2 square, respectively. And the ratio of the two forces becomes m1 r1 t2 square upon m2 r2 t1 square. According to the Kepler's third law of planetary motion, square of the orbital period of a planet is proportional to the cube of the mean distance from the Sun. Hence, this ratio can be rewritten as m1 r2 square upon m2 r1 square. That is, the force responsible for the planetary motion is proportional to the mass of the planet and inversely proportional to the square of the distance of the planet from the Sun. According to Newton's third law of motion, a force of the same magnitude must be exerted on the Sun by the planet. If the force is proportional to the mass of the planet, then it should also be proportional to the mass of the Sun as well. Thereby, the gravitational force exerted by the Sun on a planet is equal to g times the product of the masses of the Sun and the planet upon the square of the distance between their centers, where g is the universal gravitational constant. In 1798, British scientist Henry Cavendish experimentally measured the value of g, which is equal to 6.67 into 10 to power minus 11 Newton meter square per kilogram square. If 2 point masses, each of mass 1 kg, are separated by a distance of 1 meter, then, according to the Newton's law of gravitation, the force of attraction between the masses becomes equal to the universal gravitational constant g. It has been found that this force is equal to 6.67 into 10 to power minus 11 newtons. Hence, the value of g should be 6.67 into 10 to power minus 11 Newton meter square per kilogram square. Knowing the value of g, one can determine the masses of Sun, Earth, Moon and other planets. Let us see how. For a planet like the Earth, moving in a circular orbit around the Sun, the necessary centripetal force is provided by the gravitational force of attraction. Therefore, g into m upon r square must be equal to 4 pi square into mr upon t square. By rearranging, mass of the Sun can be obtained by the relation 4 pi square r cube upon gt square. By substituting the values of g, orbital time period of the Earth and the mean Sun-Earth distance, we can measure the mass of the Sun. That comes out to be 1.98 into 10 to the power 30 kg. In the similar way, by knowing the orbital period of the Moon and the mean Earth-Moon distance, one can find the mass of the Earth. Let us measure the force of attraction between Earth and a stone of mass 2 kg placed on the Earth's surface. Force of attraction between the Earth and the stone can be obtained by substituting the values of g, mass of the Earth, mass of the stone, and the distance of the stone from the Earth's center, that is, the radius of the Earth in the given relation. The gravitational force comes out to be 19.6 newtons. On the other hand, if the two masses each of mass 2 kg are separated by a distance of 1 meter, then the force of gravitation between them comes out to be 2.7 into 10 to the power minus 10 newtons, which is very small as compared to the force exerted by the Earth. Today, Newton's law of gravitation is used to determine the orbits that take spacecrafts from the Earth to various destinations within our solar system and beyond. In addition, law allows us to calculate with pinpoint accuracy of the time of solar eclipses and other astronomical events. Mass and weight. Anything thrown up falls downwards towards the Earth. Climbing upstairs is a lot more tiring than walking downstairs. Raindrops from the clouds fall to the Earth, and all of this happens because of the Earth's gravity. It was Galileo who recognized that all bodies, irrespective of their masses, are accelerated towards the Earth with a constant acceleration. He said that all objects fall with the same acceleration unless air resistance or some other force acts on them. He argued that the air resists an object traveling through it. If the material is dense and its surface area is small, the air resistance is quite small as compared to the gravitational force. Air resistance can be neglected while studying falling stones, metallic blocks, etc. Since the acceleration of an object is the rate of change of its velocity, so there is no effect of its mass. Therefore, when a heavy object and a light object are dropped from the same height, both would reach the ground at the same time. To find the truth, he did experiments with bodies rolling down inclined planes and measured the value of acceleration, which was close to the more accurate value of acceleration due to gravity obtained later. In 1686, Newton formulated his well-known Law of Gravity, according to which every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. He established a relation for the force of gravitation and concluded that the Earth attracts every other body lying near or on its surface towards its center. The term gravity is used for the force of attraction exerted by the Earth on the body. When a force acts on a body, it produces acceleration. Therefore, a body under the effect of gravitational pull must accelerate. For example, if we throw a ball upwards, its speed decreases till it reaches the highest point, and if we throw a ball at an angle, its speed changes throughout its motion. It shows that whenever an object falls freely near the Earth's surface without an external force, that is, under the influence of the Earth's gravity only, then it is accelerated. The acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity. It is denoted by small g. Let us consider the Earth as a solid sphere of uniform density, and the entire mass of the Earth is concentrated at its center. If an object of mass m moving freely near the Earth's surface Neglecting the air resistance, the only force on the object is due to gravity. Magnitude of the force of gravitation on the object is g times the product of the mass of Earth and mass of the object upon the square of the distance between them, that is, the radius of the Earth. By using Newton's second law of motion, the acceleration of the object can be obtained as the ratio of the force due to gravity and the mass of the object, which is equal to the product of the universal gravitational constant and the mass of the Earth upon the square of the Earth's radius. This is the expression for acceleration due to gravity at the surface of the Earth, which is usually denoted by the symbol g. In general, acceleration due to gravity on the surface of the Earth is equal to the gravitational force per unit mass, and its direction is always towards the center of the Earth. This is a very significant and quite remarkable relationship. Here, acceleration due to gravity g is measurable. Here, it can be noticed that acceleration due to gravity does not depend on the mass of the object on which the gravitational force is acting. For all other forces, acceleration depends on the mass of the object on which the force is acting. That is why the value of acceleration due to gravity does not depend upon whether the object falling under gravity is a light one or a heavy one. Knowing the mass of the Earth and the radius of the Earth, the value of g can be calculated as 9.81 meter per second square. On the other hand, knowledge of the values of gravitational constant, acceleration due to gravity, and the radius of the Earth enables us to estimate the mass of the Earth. This is the reason when Cavendish measured the value of universal gravitational constant, there was a popular statement that Cavendish weighed the Earth. Acceleration due to gravity on the Earth's surface is 9.81 meter per second square. But when we go above the Earth's surface, the value of g decreases. Because at a height h from the Earth's surface, mass of the Earth remains constant, but the linear distance between the object and the center of the Earth increases. The acceleration due to gravity at a height h will be equal to g into mass of the Earth upon the square of the distance of the object from the center of the Earth. On the other hand, when we go deep inside the Earth, the value of g should increase. But the situation is different, as the value of g again decreases. In this situation, the gravitational force acting on the object at depth d is due to the effective mass of the Earth's shell of radius re minus d. Let's see an interesting situation. Suppose we have a tunnel passing through the center of the Earth, starting from the North Pole and ending at the South Pole. If we drop an object in the tunnel from one end, the acceleration due to gravity decreases as we go down towards the center of the Earth. And at the center of the Earth, it becomes zero. But at the center of the Earth, the object has a maximum kinetic energy and hence it moves forward. Moment the object moves from the center of the Earth towards the other end, the acceleration due to gravity starts increasing. Thereby, the velocity of the object starts decreasing. When the object reaches at the other end of the earth, its velocity becomes zero. Therefore, it returns back. In this way, the object would show to and fro motion in between the North Pole and the South Pole. Measured value of acceleration due to gravity is different from the actual value due to some natural factors such as constitution of the earth, shape of the earth, and rotation of the earth. For example, in the formulation for acceleration due to gravity, the earth was assumed as uniform and stationary sphere. But our earth is not a sphere. It is an ellipsoid. Its equatorial radius is greater than polar radius by 21 kilometers. Because of this, acceleration due to gravity is greater at poles than at the equator. Since the radius of the earth does not change much over its surface, thereby acceleration due to gravity more or less remains constant on or near the earth's surface. Because of this, when an object is moving vertically up or downward under the gravity, its motion is similar to the uniform acceleration motion. And all the equations for the uniformly accelerated motion become valid by replacing acceleration A by acceleration due to gravity, that is g. Since direction of acceleration due to gravity is towards the Earth's center, therefore, when the object is moving upwards, value of g becomes negative. And when the object is moving downwards, value of g becomes positive. Let's solve some problems. A ball is dropped from a building 196 meter high. How long does it take to reach the ground? Here, the height is given from where a ball is dropped, which is initially at rest. Time required by the ball to reach the ground can be measured by second equation of motion as shown. In the next problem, a stone is dropped from the top of a hill 1960 meter high. What is the velocity when it has covered 1000 meters? Find the velocity when it hits the ground. Here, the height is given from where a ball is dropped, which is initially at rest. By using third equation of motion, velocity after covering the distance of 1000 meters comes out to be 140 meter per second. When the stone reaches the ground, its velocity comes out to be 196 meter per second. By knowing the acceleration due to gravity, one can measure the weight of an object. Generally, mass is commonly referred to as weight. For example, we say that an object weighs 1 kilogram, even though kilogram is a unit of mass. In fact, weight and mass are quite different quantities. Mass of an object is the quantity of matter it contains. The mass of a body is defined in two different ways: inertial mass and gravitational mass. Inertial mass is the measure of an object's resistance to changing its state of motion when an external force is applied. In other words, when a body is in translational motion under the effect of an external force other than gravity, the mass of the body measured is called its inertial mass. On the other hand, when a body is under the effect of gravity in the absence of motion, the mass of the body measured is called gravitational mass. Weight is the measurement of the strength of gravitational force on the object. That is, how heavy it is. We know that the unit of mass is kilogram, but the unit of weight is kilogram weight, and SI unit is Newton. The weight of a body of mass m is equal to the product of mass with acceleration due to gravity. Mass is an essential property of any material object, and therefore for a material object, mass can never be zero. It is not affected by the presence of other objects. An object has the same mass wherever it is. It does not vary with the change in temperature, pressure, or location of the object in space. Whereas, weight of an object becomes zero at the center of the earth, which also suggests that weight is not an essential property of the object. Weight or the gravitational force can change with location, as well as it varies from place to place on the Earth's surface and with distance above or below the ground. For example, if you're lucky to travel to Moon someday, you will find that your weight is less on the Moon than on the Earth, though your mass remains unchanged. It is 1/6 that of the Earth. For example, if the mass of a boy is 25 kg, then his weight on the Earth is 25 kg weight or 245 Newton. Whereas on the Moon, the mass of the boy still remains 25 kg, but his weight becomes 40.5 Newton or 4.1 kg weight. The weight which we actually measure is not the downward force of gravity, but an upward force exerted by the surface we stand on.